Hello, so we're going to be doing a full paper today, Unit 3 from October 2023. So look at our first question. We got exponential and logarithmic equations. So find a set of values for x with a given inequality and make sure it's three significant figures as well. Okay, so with the modulus we're going to want to have a negative and a positive version. So let's start with the positive one. I've just taken out the mod and moved the 2 over, so cancelled plus 2 on both sides, I should say. Take logs on both sides, log 2 if you want. Don't need a base. So x plus 1 is less than log base 2 argument 2.5. So from there you just, again, your general algebra, cancel plus 1 on both sides with minus 1. And you'll find x is less than, calculator out, 0.322. That's one half of it done. Let's do the second half. I'll do an extra step here at the beginning with the negative 1 just to make sure that it's very clear for you. So you take away the mods. Minus 2 to the x plus 1 is less than minus 1.5. So now we're going to change the sign and change those signs as well. Positive signs. Again, like the last question, exact same thing happening here. So just be careful with the sign change there. So x is greater than minus number here. We have log base 2 1.5 minus 1. So we would write out our range now. So our range was minus 0.415, less than x, less than 0.322. Okay? That's the first question for 4 marks with logs and modulus. So we've 11 questions, I believe, in this. So let's get moving on an Argand diagram. Shade the region. Okay, so you're going to have z. Mod z is equal to r. That's a circle. So you can see our second highlighted part there is a circle in some way with a radius. The first one was a bisector. When you've studied this, you'll kind of just know that they look like that. So as I'm writing in the green on the right hand side, that's our circle there. And again, like modulus z, we'd say is like distance to the origin. So if it was z minus 3, it's a distance of 3 to the origin. And that kind of thing. So here we have 2. So that's your circle there. And the second one here is more expansive, more difficult, I'd say. Yeah. So that's me just writing it out so you can reread it for where it's positioned on the coordinate grid. So 1 and minus 2 would be your coordinates from 0, 0. And of course your bisector is perpendicular to that. I'm going to use a straight line. Copy and paste, yeah, much better than my drawing. And from there, I'm just going to draw it. I'm going to do actually the algebraic version of this as well. You can say it's optional if you want, just to help plot it. So plotting that little straight line, I think it's important to see all these little pieces, bits and pieces. So what are we shading here? We're shading in there. Shade the region that represents that. Let me just show this though, as I said. So I'm rewriting it with like x plus iy. So that's the first highlighted yellow part there. You can see there in black. And now I'm just rewriting it out. So z is equal to x plus iy. Excuse me. And we can, from here, we can get ourselves like the equation of a circle, x squared plus y squared equals r squared kind of idea. It won't be that. You just see what I'm doing here. I'm just following what we have here, if you know what I mean. So x minus 1 squared plus y plus 2 squared, as you see, just putting in those squares. So x squared plus y squared for that part of the right hand side as well of the equation. And then multiply it all out, x squared minus 2x plus 1 plus y squared plus 4y plus 4 equals x squared plus y squared. And then bring it all down together. You can do that by now. And you can just basically go y equals at the end of this. So minus 2x plus 4y plus 5. And from there, y is equal to 1/2 x minus the 5 over 4. So you didn't have to do that part I did in the black ink, we'll say. But it's there anyway, just to show it. So you have you're clear about your straight line. And of course, like with the picture for where you shade, just check where your inequalities are going. So you can compare it to 0, for instance. So a classic polynomial question here. We're given some variables that are unknowns, and we're also given some details that will help us build two equations. And from there, generally you'll use simultaneous equations or substitution to solve or find the values here of a and b. So we can say x plus 2 means x is equal to minus 2. And of course we have 2x minus 1, which means that x is equal to 1/2. So plug in these values now for substitution. So 2 times minus 2 cubed and so on. And we have a remainder, so equals minus 38. Okay, and also for px, we have that as well. Just plug them all together there. I had that ready. I had this ready already. That part. For some of this, I'm going to have bits and pieces written out ahead of time. For little calculator bits. You know how to do them. 19 over 2. So that's a remainder. So again, a plus 2b equals 13. And from there, we can solve for this because we have a 2b and 2b in both of them. So we got 5a and 15, isn't it? So a is minus, yeah, that's right. A is minus 3. Plug it into this most simple one to do, so minus 3 plus 2b equals 13, you could say. Just make it as easy as possible for yourself when you're doing this. Especially under conditions that are stressful, like an exam. So b is equal to 8. So we sub that in. I think I wrote down one of the signs incorrectly up there. Just as I was doing it quickly. It's okay. Right, question 4. So this one looks a little bit strange. Again, we've already done a question on complex numbers. So we're going to find in the form x plus iy, with a little bit of that. Thinking of the discriminant, or thinking of quadratics in general, I think if you just look at this, you'll see that you have your, in your form ax squared plus bx plus c, you can use the quadratic formula. So let's do that. So w, we're going to have minus 2 plus or minus root. I'll do the line in a moment. Minus 2 squared minus 4 times 3 plus 1. Sorry, 3 plus I. And then 3 minus I. It looks like 1 there for a second. A nice little line there for us, and another line underneath. Looking nice and pretty. 2 times 3 plus I. That last part and above the 4ac, so let's multiply that out. You're going to get 3 times 3 is 9, plus and minus 3i, and then remember that I squared, so I times I is going to be minus 1. So be careful with that part there. So 9 plus 1, or 9 minus 1 is 10. Just for that simplification, I'll do it now. So root 4 minus 4 times 10 all over 6 plus 2i. So we're getting somewhere now. We have 2 plus or minus 6i. So 36. The root of 36 is 6, as you know. And it's x plus yi, remember. And we have 6 plus 2i, as we had already. And we're going to have simplification going on here now. We need to find the positive and negative version anyway. So let's write out the first one, like 2 plus 6i over our denominator that we have, and also on the other side I'll do 2 minus 6i. And of course, think of it like rationalizing the denominator that you did in GCSE. Well, you did it in grade 11 as well, with thirds. I don't have the space here. Just get your calculator out and do this out. I'm kind of MacGyvering it here a little bit. I've just realized I don't have enough space to draw it all this. So I'm just doing it on paper here. So we end up with 3 over 5 plus 4 over 5i. Let me just look through the rest of this. Okay. So then do the same thing on this side. So multiplying across. You could do it in 2 steps, to be honest. Just do it on paper twice and then do it on your calculator as well. I was just looking through the paper here. I'll make sure to have I have enough space for the rest of the questions properly. I haven't done it on the paper, so yeah, I'm just checking these details. It's 40, 40 minus 40. So minus 40i over 40, which is of course minus I for that one there. So that was our left hand side and right hand side there for positive and negative answers. And we found them was real as well. Question 5. Okay, I have loads of space for this one. Let's make sure we just have that now. It's important to show all the details. Find the exact coordinates. Okay, stationary points, we're dealing with dy over dx, so differentiation is equal to 0, so that's a stationary point, turning point if you want. And we have a function there. So let's just do out our usual thing with these. So you have u and v. This is going to be the quotient rule. So just do out your differentiation there. So of course the differentiated index for the first one for u prime is 3 times 2 is 6, so that 6 goes out the front and everything else remains the same. For v it should be straightforward. It's your general polynomials from last year. So do your quotient rule. V times u prime minus u times v prime all over v squared. Excuse me. All right. So just change that there. Okay, so 8x e to the 3x squared minus 1, and then minus 6. That's okay. I'm just checking the details there. You can always factor out elements of these things as well. You're trying to see what's the smallest amount, the smallest part to factor out. In this case, we have make it equal to 0. In this case, we have I'll just write the factor out part just to make it clearer. So if you have a negative exponent, you would factor that out. Something to the minus 1, we'd say. Okay, so we factor out our constant of 2, we have x, we have e to the 3x squared, minus 1 on both of them. So we have 4 minus 3x squared. And from there, we know that you can do the maths on this if you want, but e to the 3x squared minus 1 is equal to 0. There's no solution. Usually, but just check it anyway. X squared is equal to 4 over 3, so we have root 4 over 3, which is 2 over root 3. I'm just going to rewrite that. I just did that backwards. 3 over 4. Okay. Which is 2 over root 3, and 2 times root 3 over 3 is it simplified again. Rationalize the denominator. Okay, from there we have a positive and negative version of that because we found the root of it. So I'll do that below. And so if x is equal to 0, let's just solve this. X is equal to 0, so plug it into the original equation that we had. So y was equal to e to the 3x squared minus 1 all over 1 minus x squared. So just make e equal to 0. X equals 0, and you'll get your value of e to the minus 1 there. So those coordinates were 0 and e minus 1. E to the minus 1, sorry. And second and third one here, plus 2 root 3 over 3, or minus. Same thing, plug it in. So y equals e to the 4 minus 1 all over 1 minus 4 over 3. And calculator out for this bit, minus 3 e to the 3. And there's those values there. A bit clunky looking, but it's fitting at least, just about. The next one's going to be the same answer. Do it out anyway. E to the 4 minus 1 all over 1 minus 4 over 3. Exact same answer, so just be careful there. But the x value is a negative, the y is the same. Again, look at these in terms of these kinds of questions where like iLate, strategies of integration as well. You'll have that kind of thing. You should do you'll do exponentials after you do trig and after algebra and after logarithms. Anyway, trig identity. Okay, we have to rewrite this. We've cotangent and cosine 2 data, so there's 2 things we need to do. We need to get all of our bits in sine, which is nice. It's nice to know that. So I've made cotangent into cosine squared over sine squared, and then cosine 2 data, we'll change that in a second, won't we? It's a double angle. I'm going to multiply across, of course, with sine there, just to do that. Just find the easiest route where possible. So we multiplied sine across there. That cosine 2 data, again, we want to get everything in sine. So I've changed the first one there to 1 minus sine squared data from your previous grade 11, and then also this one to 1 minus 2 sine squared data, which is a double angle formula, one of the 3 for cosine. So I've changed 2 things there. You can see in the green I've highlighted it. And then just simplifying stuff down. I'm skipping there, wait. Let me just not do it. Let's just do it very clearly. So 2 times 1 is 2. So minus 4 sine squared data, and that times sine again in the next step. I won't skip the steps. 1 minus sine squared data plus 2 sine squared data. That's times sine. So expanding brackets here, as you see. Minus 4 sine to the 4. Careful there. Data equals 4 sine squared data. So we end up with 4 sine to 4 data minus, I think, let's check that again now. I just did it out quickly. I always put minus first, and I can do a little, I think it's a plus actually. Let me just check it one more time. I just did this in my head. There, it is plus. Yeah, that makes sense. And that's it. The answer of course above was a plus. So I had to just check that again. Just making sure, 100%. So the right hand side was equal. Okay, so hence we will definitely be using something from the previous question because of that word. Solve it, and we have a range between 0 and 360 degrees. Let sine to the power of 4 data equal y squared. So we're doing a kind of a disguised or hidden power, hidden quadratic is what it called last year when you did these. So 4y squared plus 3y minus 1 is equal to 0. Pretty straightforward to solve there. This is pretty much the same as grade 11 when you think about it. So y is equal to 1 quarter or minus 1. So sine squared theta equals 1 quarter. So that's of course plus or minus 1 half when you root it. And sine squared is root minus 1. We have done some complex numbers, but we're not doing it here. So no solution. We still have two answers to look at. I'm going to draw a little graph. Where's my thingamajig? Let's just draw it like that. Yeah. So you're going to have half. You probably know half is 30. So 180 minus 30 is 150. And then again, 210 and 330. You use your cast unit circle or use your graph to kind of help you there. Just remember with sine, cosine, and tan, they're a little bit different like that, but they make sense. Like you take away from 360 for cosine and you add on 180 for tan. And if you're using radians, again. So for sine, you subtract your angle from 180, so pi. For cosine, you subtract it from 2 pi. And for tan, you'd add pi each time for those trig functions. Onward, we're going to do question 7. This is implicit differentiation, unit 4. And we're given something, so we have to show that it's this. There on the right hand side is just the way these work with x and y. So implicit differentiation is always a little bit tricky looking, I suppose. Just the way it's used. It's not that difficult though, when you actually come down to do a bunch of them. So I'm just writing out here the derivatives of these. So we have y's mixed with x's. And so to deal with that, we add in a dy over dx with our y's. And then from there we can simplify it out. So I've got my dy over dx. Those parts have a 2y plus 3. And then of course I've minus 3x squared and 6x. And divide your 2y plus 3 on both sides. Okay, so hence, so using apart from there, so we have a minus 3x squared plus 6x over 2y plus 3. Tangent is parallel to the x-axis. So again, dy over dx equals 0. When you have a fraction equal to 0, of course, you cannot have denominator. Your numerator has value. You can't divide by 0, put it like that. X squared plus 2x equals 0. So factor that, x plus 2 and x equals 0. So x equals minus 2 and x equals 0. Let's plug these in. Plug them into your original equation. So where x equals 0, we have it there, yeah, plus 3y. Plus 3 times y equals 4. And you get, of course, y squared plus 3y equals 4, or minus 4 equals 0, and then solve that. Expand the brackets there, y equals minus 4, and y equals 1. So there'll be a set of coordinates. You have 0, minus 4, and 0, 1. Now we'll do the same for x equals minus 2. So plug it in, same thing again. Plugging it back into the original, so x cubed plus y squared plus 3x squared plus 3y equals 4. And again, similar but not the same. So y squared plus 3y equals 0. So y equals 0 or y equals minus 3. Again, you have x value of minus 2, so for these ones it would be minus 2, 0, and minus 2, minus 3. So we'll write down our full values now at the end. After this, I'm just showing the details there that I was speaking of already. 0, minus 4, or 1, whatever order you want. And then minus 2, 0, minus 2, minus 3. From those other set of values. Okay, so there's the values there. in that order. On to question 8, we have a differential equation. Sometimes these will look a little bit scary, but they're okay. It's given that y is equal to 0 when x is equal to 2, so we'll need that in a moment. Expression for y in terms of x. So we're going to get some stuff on different sides. We want to get our y's together and x's together. It's the simplest way of looking at it. Non-mathematically, just visually. So 1 over cosine squared 3y dy, so we move our dx over as well. And of course we have integration here, so integration sign is in front of all these. Again, 1 over cosine is sec squared, so to put that in, nothing to change on the other side yet. We're just going to integrate it next, I can see. So sec squared 3y is 1/3 tan 3y. And then minus 4, so minus 1 over 4 e to the minus 4x plus c for integration. So y is equal to 0 when x is equal to 2, plug it in. So we got our y values there and x values to be plugged in. So 1/3 tan 3 that's going to be 0 anyway. So if that's the case, then c is c minus 1/4. So c is equal to 1/4 e to the minus 4 times 2 is minus 8. So just write that out there just to make it very clear. From there you can plug that in, of course, to complete our equation. And we can simplify it down, perhaps. So we can get it down to y. Y is equal. So yeah, dividing, we have 1/3, so we multiply across. So what else? Tan, just tan, arctan or tan to the, not to the minus 1, but the way it looks there is the angle, isn't it? Nothing changes there, just put it in brackets and then divide by 1/3 for the rest of it, because you divide it on 3 on both sides. So you'll have 1/3 tan, or arctan, sorry. Tan, which is minus, here, which is minus 1. It's not a power. Remember that. And that's a fairly straightforward one, to be honest. So we separated our values, our variables, I should say, and then integrated. Oh, a nice one here. So we've partial fractions, and we have the square inside the bracket. So be careful with the one of 4 types of question you could get. So our numerator is equal to ax plus b in brackets plus c. It could be, it could change. It could be a plus bx plus c. So the bx plus c is in brackets if that power was in the second, the second brackets, we say. So having done that out, we multiply by our denominators there just to play it out. So x is equal to 2, we have that. That's really the only thing we can use with this particular type of question, with partial fractions, with the square inside. So just doing it out, we can find c. 68 minus 14 plus 16 equals 14c. C is equal to 5 there. We've done that out. And for the next one, often you'd use another variable there that you have, like x is equal to something. But we don't know, so we're going to make x equal to 0. Or x equals to 1, minus 1, but x equals 0 is probably our best bet. And again, coefficients can be equated and things like that. So it's a bit longer when you're doing this out, because you don't have to write out 8 times 0. Maybe you probably know that, but just it should be clear. 2b plus 2c, and we know that c is 5, so that's 10. So b is equal to 3. X is equal to 1. Let's do that one. And we put all our bits together, so we have 8 times 1 plus b, 2 minus x is 1. And you're just putting in all those little play pieces, so it's a little bit longer when you're doing some of them now with this particular example. But you already have the constants of b and c. I need to write that in again. Yeah. Now it's clear. Now it's straight. Yeah. Okay, so 17 minus 7 plus 16 is 26. a plus 3 plus 25 in this case. 5 times c is 25. And so I'm doing it in my head before I'm writing it, just to make sure. So 5c, so I know it's 3 and 5 in there. Let's make it clear with our highlights. There we go. And c as well as yellow. Green and yellow. Or is it blue or green? I'm not sure. A is equal to minus 2. Okie doke. So minus, I'll write it up there, minus 2x plus 3 all over brackets 2 plus 3x squared, and then plus separate fraction 5 over 2 minus x. Okay, that's question 9, part A. Part B often is an integration question, or in this case, binomial expansion. So we're going to take these two terms that we have from the previous answer, and we're going to do them separately. Remember, same as the quotient rule, product rule, combination, in terms of you can change your denominator with a little twist on with a power to make it product rule instead of quotient rule, and in this case the same thing. Doing binomial expansion, and that's what we did to the first one there. And the second one will be 5 over 2 minus x, so 5 times 2 minus x to the power of minus 1. That's our second one we're going to write down now. Okay, first one, I need to change the constant in the first one. So 2, I need the 2 to become 1. So we do 2 to the power minus 1, which is a half, and then 1 plus 3 over 2 x squared. So that bit has to be changed. We can only do it in that form for this particular technique. So put the half out front, and then everything else is straightforward. From there we can expand it out. So minus 1 times 3x squared over 2 plus, I need to just get up to an x cubed. So third. So I think I have that there. Nearly. So multiply it out. Minus 2x times 1 minus 2x times that bundle of terms there, and again 3 times 1 and 3 times the third term there as well. We end up with a square there, so we'll have a cube. And just a half times that, a half times this, a half times that. Put them in a certain order, I think. I'm looking at it now. You're best off putting them in an order like, so 3 over 2, that's our first one, minus x, minus 9 over 4x squared, and then the other one I did there was 3 over 2. Just checking, making sure. There's our first one done. Second one. It's going to be a bit longer, this one, because the details are less. So 4 times 2 to the minus 1, because I need to change the form of that. So instead of 2 minus x, I need 1 minus x over 2. And from there I can start multiplying it out there and using the binomial expansion. Again, 5 over 2 is 5 times a half. So minus 1 over x, minus x over 2, sorry. Can I fit that? I can't fit this. It's going to look a bit clunky. Let me move it over there. Even then, I think it's probably a bit tight. So plus again, so I'm going to have 2 more terms here. So minus 1 times minus 2 over 2 factorial, which is the same as 2, times minus x over 2 squared. And then again, minus 1 times minus 2 times minus 3 all over 3 factorial, which is 6, times minus x over 2 cubed. And that's all we need. And so 1 minus x over 2, minus and minus is a plus. Just be careful of your signs as well. X squared over 4 and x cubed over 8. Plus dot dot dot. Goes on forever. So again, just try and put them in the same way. So 5 over 2 plus 5 over 4x plus 5 over 8 x squared plus 5 over 16 to the power of 3 cubed. And we just add them now. So we're going to add our first and second parts. Use your calculator, of course, if you want, for all that stuff. So 1/4, or x over 4 if you want, minus 13 over 8. I'm just doing this in the calculator, pop it out. Quickly quick. There's two fractions. You don't have to put in the x squares, of course. Just do the little coefficient, the numbers, we say. So plus 29 over 16. Okay, state the values for validity. So we've done validity tests with this before. So the exact value. So what we have here is, you have to go back to a certain point now to check this. It's at the point where it's 1 plus, you know, where we did the second step. So it's 3x squared over 2 is less than 1. And minus x over 2 is less than 1. And the mod symbols around those as well for positive value. And again, you'll end up with x is less than root 2 over 3. And the second one, it's not valid. So it takes away this the negative sign anyway. So x is less than 2. Our value is root 2 over 3. There we go. We have a curve, y is equal to x times x to 2x. Okay, this is the kind of question where you have to pick out which technique do I use. So differentiation and integration, you're going to come across sometimes these. I think it's in parts. So u and v, let's do our thing now. We're definitely like multiplying. So you know the product rule is the first time you learned this. So we have x and cosine 2x, but we have to do our v prime. Let me just check again what I'm doing here. Okay, just checking that stuff. So x is equal to pi over 2. So minus 2 times pi over 2 sine pi over 2 times pi over 2 is pi. Same for cosine there, just pi. So 2 times a half is 1, you know. Cancel that out, so you get 0, so you get 1, minus 1, yeah, just a minus. So 0 and minus 1, so m, gradient. The gradient function, the gradient is minus 1 there, isn't it? Check your graph if you want. You can see that cosine is minus 1 at pi. There's the product rule there, okay. So finding y. Y is equal to pi over 2 cosine pi. So when you plug in the x value, as in 1/2 pi, you know, pi over 2. And that's it, it's minus pi over 2. So you can find an equation then. So find the equation of the tangent, y plus or minus. So y plus pi over 2, y minus pi over 2. So it's y minus minus, y pi over 2 equals minus x plus pi over 2. So yeah, minus x. Just making sure. Back and forth. Checking it. Find the exact value. So we have to value of the area. We've integrated in some way here. We've used product rule for the previous question. For the equation of the tangent is often to do with, you know, obviously to do with differentiation. So the value here, so x, if x is equal to 0, you know, when it crosses the axis of where we're looking, so x cosine 2x equals 0, cosine 2x equals 0. So 2x is pi over 2 and 3 pi over 2. You can check your graph as well. And so x is equal to pi over 4 and 3 pi over 4. And we can use in parts. We're going to use integration in parts here. So we've u's and v's. Just be very careful that you do your u equals x, let's say here, but then you do your v prime, which is what you're given, which is the cosine 2x. Just write that out first. We don't need a diagram really, just to show it. So u is equal to x, v is equal to, just leave that for a second if you want, and your v prime is what you have, so cosine 2x, and you're going backwards in this sense. So minus, 1/2 sine 2x. Okay, from there we can do it. So you have your formula x times bracket half sine 2x close bracket minus integral between boundaries of pi over 4 and 0 and half a sine 2x again. So integrating that. And from there you get half x sine 2x, so that's straightforward. You can plug in your value then of pi over 4 and 0 and 1/4 cosine 2x. Okay, and calculator, do the job, so pi over 8. And then 1/4. 1 over 4. And again, you could use your ILATE. You're kind of checking what technique. We didn't really have to do much there because it's just, but you do trig, down after doing logarithms and so on. So unit circle, unit vector, okay, I've changed that. We're looking for R, so L is, okay, let's just highlight all this. There's a lot of details. I'm going to write these as column vectors as well. This is way easier to look at. So R is equal to, put our double bracket, you're doing bracket stuff here. 1 minus 2 and minus 3 plus lambda minus 1, 1, 2. So we have a position vector and a directional vector there. That's like the vector equation. That's what they look like. You could have lambda or mu or anything, T, S, whatever. You see a whole bunch of things, A, B, whatever. A and B have a positional vector. Let's just write that down as well. So minus 2, 2, minus 1. And 3 minus 1, 1. I have that there. Okay, that's good. So the magnitude of the directional vector, so minus 1 squared plus 1 squared plus 2 squared is root 6. So root 6 is there. So again, how do you write out your unit vector? So it's 1 over root 6 times the original directional vector. So 1 over root 6 times minus 1, 1, 2, in that sense. And when I say these, I mean IJK. So when I'm saying 3 numbers in a row like that, it's the IJK of that, in the way you've learned, I'm sure. Just in case. So that was a unit circle in direction of L. Next vector equation, like the thing I just spoke about there. So AB, and of course, the vector of AB is B minus A. I'll write that on the right hand side there. So 3 minus 1 plus 1 minus 2, 2 minus 1. And again, add them up for the directional vector. I just rewrote them there anyway. 5 minus 3 and 2. And that's it. So you just need to pick a point, which we're given. Sometimes you just have one. But we have A there, so R equals minus 2, 2 minus 1, which is a point on A that we were given. And so M passes through A and B. And again, I'm just using mu. That's like the little U looking thing. And that directional vector that we had there is what, I'm just writing it there anyway. As I did. Determine whether the lines L and M are parallel. So, yeah, okay, there's different techniques for this. So, skew is not intersecting. And intersect, of course, is the name. And parallel, of course, means they don't meet either, but you have to test. It's like a little test to reach. This is the last question. Excellent. So just start with the first one, parallel. If they're parallel, we can just test this by seeing if something is a common solution, if they have a commonality in one of their answers, in the way you put these together. So let's take a point like minus 1, 1, 2 for, you can use it, look at your previous answers as well. So the directional vector minus 1, 1, 2, and then comparing it to what we just did, so 5 minus 3, 2, that was part B. So that'll tell us, you can use A or B or T or S, whatever. But it's just so you have a variable in front to solve. Minus 1 is equal to 5A, A is equal to 1/5. Again, same thing for the next one. A is equal to minus 1/3, and then A is equal to 1. So there's no commonality solution there, so they're not parallel. So they're not parallel there when you compare those. Next one is going to be a bit more difficult when you're doing intersections. You're going to need the full part. So looking at the very first part of this question where you had or equals like 1 minus 2 minus 3 and then lambda times these parts as well, you kind of have to use all of them. So like each of them separately. So I plus lambda minus I, you'll take that on its own. So it's like 1 minus lambda. And that kind of thing. I'm trying to put this out. Give me a second here. That doesn't work. I was trying to do a thing there. Okay. So I'm just doing a freehand. 1 minus 2 minus 3. So 1 minus lambda minus 2 plus lambda and minus 3 plus 2 lambda was what we saw up there. We're going to equate it to answers we have as well. So you see from part B, you can see just above, I'm writing them out as well. So the last one there is minus 1 plus 2 mu. You see? From there you can again just separate them out. So the first one, and again you won't get an answer specifically, you're just going to get an equation. Like 3 equals lambda plus 5 mu. And again, do that for the other two. And then when we have the 3, then we'll just use the first two, I suppose, to solve for the third one. See if there's intersections. If they are intersecting, then obviously they should have a common answer. You know, they intercepted. They crossed each other. So there's our two. We just use them. So simultaneous equation here. We have lambda on both, so cancel that out. So you get minus 1 equals 2 mu. So mu is equal to minus 1/2. Okay. Again, mu just, it looks like an M there the way I'm writing it, but it's like a U that has a bit of an edge on the front of it. It's a Greek letter. Mu is equal to minus 1/2. Now, let's see if this works for the third one. If I plug that number in. Yeah? So like for lambda as well, you know. Lambda is a different, let's check it. 3 times minus 1/2 equals lambda minus 4. So lambda is equal to 11 over 2. So they're not there. Let's sub it into the k. Let's sub it into the other one. So minus 3 plus 2 times 11 over 2 equals minus 1 plus 2 times minus 1/2. And you get 2, so 8. Yeah, 8 is not equal to minus 2. Just making sure, yeah, 8 is not equal to minus 2. There's no intersection. So they're not parallel. There's no intersection. So just